So we're going to go through a method of problem solving that involves altering your reference frame to simplify your problem. Right? So if we wanted to call that something, we could call it altering your reference frame to simplify problem solving. So what we'll do is we'll start with a simple problem. We're going to have two objects. Let's call it person A. And over here, person B. Person A is going to run towards person B with a constant speed of 6 meters per second. And person B is going to run towards person A, the opposite direction, with a constant speed of 4 meters per second. And they're going to start at a distance of 100 meters apart. And what we want to find out is how long will it take them to meet, to crash into each other. So we're looking for the time it will take for them to meet. Obviously, they will not meet in the middle because we know that one is going a little bit slower than the other. So they're probably, obviously, this guy going at 6 is likely going to cover more distance than the fellow going at 4. So they will probably meet somewhere a little closer to the right-hand side of the situation. Okay. So there's a number of ways we can do this. We could crunch out all kinds of algebra, but what we want to do is we want to adjust the reference frame. This is kind of like putting the entire scenario on a conveyor belt. Our goal, so let's put down here solution, so we understand that we're working on that. Our goal is G-O-A-L. Our goal is to make one of the objects stand still. That's basically the strategy. In other words, we want their velocity to be 0, and of course their acceleration has to be 0 in order for them to be standing still. So we're going to move the reference frame. Think about being on a conveyor belt, and if you have a conveyor belt, like at the airport where they you can walk along the fast-moving sidewalk. Let's just draw a picture here of a conveyor belt. And if you have a person who is walking on the conveyor belt, or running on the conveyor belt, let's say the conveyor belt is moving to our left and the person is moving to the right. And you are standing over here on the sidewalk watching, or on the cement. If the person isn't moving and stands still, then obviously you would see the person move to the left as the conveyor belt carried them past you, right? If they ran in the opposite direction, moving to the right, then what would happen is the speed at which they move would appear different because of the conveyor belt. So let's say this person runs at 6 meters per second, and the conveyor belt is moving at 2 meters per second. The combined effects of those two speeds would cause the appearance, from your perspective down here, that the person would be moving past you this way at 4 meters per second. You would add the two velocities together, right, to figure out how they would be moving. So what we want to do is we want to set up the same scenario, except we want to make it on purpose so that the person who's running is going to run exactly the same speed as the conveyor belt, 2 meters per second this way. And we're going to move the conveyor belt at 2 meters per second this way. So now, from your perspective, the person is going to appear to be staying in one place. Their little legs will be moving around as they sort of jog on the spot. That's what it'll look like to you. But effectively, by doing this, relative to where you are, relative to your position, their velocity is now 0. So how do we put a conveyor belt under the problem that we did before? Well, what we do is we pick one of these that we want to be the one who's apparently standing still. And it makes sense that if we choose the one moving to the left, it helps a lot because then we don't have to worry about negative displacements and negative velocities. So we're going to choose person B right here, and we're going to try to make person B move to the left. Or sorry, we're going to try to make him stand still, right? He's already moving to the left. So to make him stand still, what I would have to do is I would have to add 4 meters per second to his velocity. Why am I adding it? I'm adding it because if he's moving to the left, his velocity is a -4, isn't it? So I'm adding 4 to his already -4 velocity, which means that now, compared to where I'm looking, his velocity is 0. So I've put him on a conveyor belt that's moving at 4 meters per second to the right. But the trick is, just like with an equation, you have to do the same thing to both sides. You've got to do the same thing to everybody in the reference frame. So that means that I must add 4 meters per second to the other person as well. You've got to be fair. Which means that person will appear to be moving even faster, 10 meters per second. Another way to think of this is that this person appears to have the combined speed of both, the 10 and the 4. So what that means is I have new information. If I start to consider what I have, let's take person A, right? Person A now had an initial velocity of 6 meters per second, but I've added 4 meters per second because of the conveyor belt, correct? Which gives him 10. So I'm just rewriting what we had set up above so we can work with it. What else do we know about person A? Well, there's going to be a certain distance that person A is going to cover, and there's going to be a certain time that it takes. So we'll come back to those two things in a minute. Let's look at person B. Person B had an initial velocity of -4 meters per second because he was going to the left. Don't forget the direction. So what I did is I added 4 to him as well. So I've done the same thing to both. 4 meters per second being added, which doesn't change anything, just changes my perspective. But that means 0 is what he appears to be moving for me. And he will also have a certain d to cover and a time. But let's think about this. If he is now moving at 0 meters per second, how much displacement or distance is he going to be able to cover? Absolutely none. So he's no longer moving, so his displacement is 0. If his displacement is 0 and the total distance between the two was 100 meters, then person A then, stands to reason, has to go how far if they're going to meet? 100. He's got to cover the whole distance. Otherwise they won't meet. So effectively he will cover 100 meters. And now, I don't even have to worry about this. I can do a simple equation, d equals vt, because it is a constant speed scenario. And I'm doing this for person A because he's running the entire 100 meters. He's running 100 meters to the right, so I'm choosing a positive number here. Right? You always have to consider direction. His speed is 10 meters per second, and I want to find the time at which it takes. This becomes a very simple solution. Obviously 100 divided by 10 is the time, so the time is 10 seconds. So this becomes a very convenient way to address what could have been a more complicated problem, but it's a very easy way to address it by making the person B stand zero, become 0. We could have solved the problem also by making person A not move either. And if we did that, we would have changed the numbers a little bit. What you'll notice, though, is that instead of 100 equals 10 meters per second, we would end up with negative 100 because person B is moving to the left, and person B would have a negative velocity of 10. But that still works out to the same answer. So it doesn't matter which way you do it, it still works. I like, as a general rule, to pick the guy moving in the negative direction if possible, because it eliminates the problem of forgetting the negatives here. One more thing, you can also do this if there is an acceleration involved. Basically, what you do is you, choose someone to stand still. Someone or something, doesn't matter. Have a 0. And then, number 2, you add or subtract from their velocity as needed. As needed. So whatever you have to do, if you have to add 7 or subtract 5 or whatever you need to do to make it equal to 0. And then you also add or subtract to their acceleration. In the very same way. So we'll do a quick example of that in a second. And then at that point, you can solve the problem. I guess step 4 would be do the same to the other. You have to do the same to the other. So he's on the conveyor belt too. To the other participant, let's say, in the problem. So if we were doing one with an acceleration, we'll just do it very quickly. I'll show you how fast you can actually do it. Let's just take our original scenario, and let's take person A, and instead of running at, well, let's keep him at 4 meters per second. And then let's say person B isn't running at a constant speed. Let's say person B is running with an initial constant speed or walking at 1 meter per second, but then also is going to accelerate. So his initial speed is 1 meter per second, but he's going to accelerate at 0.5 meters per second squared.
For the interruption teachers, we found like those students whose last names begin with the letter M through Z, it's grade 9 only, so you should be to the small gym, that's grade 9, last name M through Z. Thank you.
And I have to change this arrow because I had it drawn it the wrong way, so we have to make sure we've got the arrow in the right place. Got to change my thickness. And there we go. Okay, so this arrow has to be changed right here. All we do is decide who's going to stay still. So we're going to make person B right here stand still. So I see he has an initial speed of 1, so I subtract 1. And I see he has an acceleration of 0.5, so I subtract 0.5. And now both of these work out to zeros. And I do the same on the other side. This particular person has a speed of 4 meters per second, so I subtract 1 meter per second, which makes it actually 3 meters per second. Right? So, oh, wait a minute. Let's see, we made an error already. Let's go back. That's why we do this. Not subtract 1. My mistake. See how easy it is to make these mistakes. So you have to be extremely careful about direction. This is to the left, so this is a -1. And if he's accelerating to the left, it's a negative. So what I really want to do is add these numbers, don't I, to make them equal to 0. Don't forget direction, as I just did. Don't forget direction. Okay, which means over here, since I'm adding, I want to add, and this won't be 3, it'll actually work out to 4. So 4 meters. 5. Let's add that. That's the beauty of live recording. You get to see all the mistakes. 5. So that makes more sense. But this person also, we have to consider what to do with the acceleration. If I added an acceleration to that guy, I've got to add an acceleration to this guy. Now his initial acceleration was 0 because he wasn't accelerating. But my conveyor belt is. My conveyor belt is accelerating. So I also must add the 0.5 meters per second squared of acceleration to him, even though he had none in the beginning. So that basically means he has an acceleration of 0.5 meters per second squared. So even though you don't see an A there, if you're adding or subtracting an A to the other guy, you've got to do it the same to him. Okay, now let's look at this scenario. Well, this is the only guy that's moving. So I don't even need to do any math for person B because he's not going anywhere. So I simply go D. Now this has got an acceleration in it, so I can't use D equals VT. Right? But I am looking for time, so I can use D equals V1T plus a half AT squared. And the distance is again 100 meters. He has to go the whole way because the other person isn't moving. His initial speed, though, will be the 5 meters per second instead of the 4 because I've added 1 to the reference frame. So 5 meters per second times t, and then this will be plus 1/2 of the 0.5 for the acceleration. And you can see what happens here. We're going to end up with the quadratic roots to solve. Maybe somebody could start punching in the numbers while I'm writing this down so we could get the actual numbers. While I simplify this, 5t plus a half times a half, I think is a quarter, t squared. So if we write this as a quadratic roots, let's just get that, 0.25 t squared and plus 5t. And if I move the 100 to the other side, it will become negative 100, and I leave it as 0. Okay. And did anybody QRF? And see what we get as an answer? So we won't do the QRF because I think you can handle that. T then equals, do we have a number? We don't have a number, so we have to do the QRF anyway. Oh, good review, I guess. Let's go back then. If we're doing QRF, I'll do it over here. Negative b plus or minus the square root of b squared minus 4 times a times c, which is negative 100, all over 2a, 0.25. So if we crunch out some numbers here on the calculator, 100 times 0.25 times 4 equals, so we get 25 plus 100, so it looks like negative 5 plus or minus the square root of 125. And that's going to be divided by 0.5. So the square root of 125, we know that it's about 11 something. So it's negative 5 plus or minus 11.2 over 0.5. So we get two possible answers, but because we are solving for a time, and negative time doesn't have real significance in this situation, we'll just look at the positive answer, which is negative 5 plus 11.2 over 0.5, which comes out to negative 5 and 11.2 equals divided by 0.5. I'm getting about 12.4. That doesn't make sense. Is that right? 12.4 seconds. A little bit longer than last time. And you might say, how come it's longer if there's acceleration? Well, it's because he started off with a very small speed. And in the time it takes for him to meet, he's not going to get going maybe fast enough. Whereas in the previous example, he was moving at 6 to the left. So that's okay. That looks like a reasonable answer. So that's how you do the reference frame adjustment. put everybody on a conveyor belt to make one person appear to stand still, and therefore you can get a much simpler solution, and the math is a lot easier if you can get that to happen for you. So it's worth practice. So